In this video, we're going to talk about semiconductors and band theory. So to understand how semiconductors work, we have to think back to molecular orbital theory, and that was all the way back in Gen Chem 1. So in molecular orbital theory, when atoms bond, what happens is that their electron orbitals will overlap, and that's how you form bonds, and that's how you form molecules. Now, in band theory, when you have atoms in a solid, in a crystal solid, all of the orbitals of these atoms are going to be overlapping, and these orbitals are more or less spread out over the entire crystal. So the crystal is really just one big molecule. Now, to think about this, let's imagine that we have a molecule made out of lithium atoms. So in our first scenario, we only have one lithium atom. Each lithium only has one valence electron, and if you have one lithium, you only have one energy level. So you put your electron there. Two lithiums, you get two energy levels, and you put both electrons on the lowest energy level. Three lithiums, three energy levels, two in the lowest, one in the next lowest. Four lithiums, four energy levels, two in the lowest, or four in the lowest rather, nothing in the highest. And as you add more and more lithiums, you're going to be adding an energy level every time you add a lithium. And you'll have these energy levels which are occupied and not occupied. So we call the occupied orbitals valence band, and we call the empty orbitals the conduction band. Now, as you go to more and more lithiums, you'll get more energy levels, but the distance between the energy levels will basically not exist anymore. So instead of discrete individual energy levels like this, you'll get just a long, big energy level. One half of these energy levels will have electrons in it, and the other half will be empty. But since the energy level is so small, electrons are free to move to different bands. And remember, these energy levels or bands are just spread out over the crystal, which means electrons are free to go wherever they want. And this means that these material are really good conductors of heat and electricity because let's say you have metal and you put electricity through it. The electrons are free to flow through that material because the energy gaps between each band are very small. While if you have a material that is not good at conducting electricity, let's say wood, well, wood has energy bands that are very big. So you use electricity with wood and the electron can't move. You did not put in enough energy to move between your different energy levels. Now, for semiconductors, the gap between your valence and conductive bands, that's not negligible. It actually exists. And we call that energy gap the band gap. And we talk about band gaps in terms of electron volts. Electron volt is another measure of energy. So something that's an insulator, you have a band gap that's very large, like that wood I was talking about. So electrons cannot move between bands. So you do not conduct electricity. While semiconductors, the gap between these bands is small, and so they can conduct electricity. And this is especially true with higher energy, or higher temperature rather. The higher the temperature, the easier for these electrons to move. So we can just look here at this table. Carbon has a big band gap insulator. Lead, tin, basically no band gap, so they are very good at conducting electricity. Silicon and germanium, they have a middling band gap, so these are your semiconductors. Now, to make semiconductors better at moving electrons and conducting electricity, you can do something called doping. Doping is when you add a minute amount of impurities that result in more electrons in your conduction band. So for silicon, as we saw in the previous slide in that table, the band is actually quite large, so it's not the greatest electrical conductor. However, if you take silicon, you add a little phosphorus to it, the electrons become mobile and you can conduct electric current. We call this an N-type semiconductor because you are carrying negatively charged electrons. Or you can dope silicon with gallium. You create holes of empty spaces. These holes allow the movement of electrical current because now your electrons can move between the holes. This is called a p-type semiconductor because you can think of each hole as positive charge. So by adding electrons with phosphorus, you are making an n-type semiconductor. By adding holes with gallium, you're making a p-type semiconductor. And if you know anything about electronics, you know that they're made out of silicon chips. So these silicon chips have 1,000,000 of these p-type and n-type semiconductors right next to each other, which are called p-n junctions. And this is how we conduct electricity in our electronic devices, by doping our semiconductors in a way to have an n-type right next to a p-type. And that is it for this video. I will see you in the next one.